In earlier lessons, we learned that towards the end of the 1800s, several experimental observations were found to be inconsistent with accepted theories of physics at the time. This led to the development of what are now considered as the two pillars of modern physics, relativity and quantum mechanics. The older theories, which are typically taught in introductory physics courses, are now referred to as classical physics. In this course, we will focus on quantum mechanics, which was invented as a result of the failure of classical physics to adequately account for the behavior of very small particles like electrons, atoms, and molecules. In this lesson, we will start with the postulates of quantum mechanics. A postulate is a basic assumption of a scientific theory. You could summarize a theory by stating its postulates. Because postulates are the simplest ideas that make up a theory, you cannot derive or prove them from anything simpler. However, postulates of a good theory are generally inspired by known facts and failures of older theories. You just don't make up postulates out of nothing. For example, quantum mechanics is inspired by the experimental facts that were found to be inconsistent in classical physics. As we go through the postulates of quantum mechanics, you may find them somewhat counterintuitive. However, you need to keep in mind that the reason quantum mechanics was invented in the first place is in order to explain things that didn't make sense. Classical physics makes a lot of sense since it is based on our experiences with everyday objects, that is, with the macroscopic world. But there's no reason why the laws of physics that describe everyday objects should apply to the atomic world. Ultimately, the test of a theory is how well it agrees with reality. For quantum mechanics, consistency with reality is best seen in how well it agrees with experimental observations dealing with the interaction of light with atoms and molecules. Here's the first postulate of quantum mechanics. It says that for any system, there is a mathematical function represented by the Greek letter psi. Psi describes the state of the system that is called the state function. Psi is also commonly called the wave function. All accessible information about the system can be obtained from psi. In other words, if there's anything you want to know about the system, you can extract that information from psi as long as Mother Nature allows it. Psi depends on the location or coordinates of each particle in the system as well as time. Mathematically, we express this idea by writing psi equals psi, open parentheses, q, comma, t. We read this expression as psi is a function of q and t. Here, the letter t represents time, and the letter q represents the coordinates of each particle in the system. Think of Q as an abbreviation for one or more variables. For more chemistry applications, we are not concerned with what is going on in the nucleus, so we can generally just treat the nucleus as one particle. True or false? If we know the wave function for a particle, then at any given instant, we can predict exactly where the particle is located, as well as how fast and in what direction it is moving. This statement is false. Knowing the exact position and velocity of a particle at the same time is a violation of the Heisenberg uncertainty principle. Nature does not allow us to know this information. It is not accessible to us. We cannot get this information from psi. Suppose we're dealing with a system that consists of just one particle, and we restrict the movement of this particle to just one dimension, the x-axis. The state function for this system depends on how many variables. The state function is a function of the location of the particle and time. We only need one coordinate, the x-coordinate, to specify the location of the particle. So the state function depends on two variables, x and t. What if a system consists of two particles that are constrained to move on a plane? The state function depends on how many variables. On the xy plane, we need two coordinates to locate each particle. So the state function psi depends on the x and y coordinates of particle 1, which we can write as x1 and y1. It also depends on the x and y coordinates of particle 2, which we can write as x2 and y2. And it also depends on time, t. So the state function depends on a total of 5 variables: x1, y1, x2, y2, and t. The wave function for a helium atom depends on how many sets of coordinates. We need one set of coordinates for each particle in the system. A helium is made up of 3 particles. These 3 particles are the nucleus and the 2 electrons. So, psi is a function of the coordinates of the nucleus, which we can abbreviate as q sub n, the coordinates of electron 1, which we can abbreviate q sub 1, and the coordinates of electron 2, which we can abbreviate as q sub 2. Note that we count the nucleus as just one particle. Of course, psi also depends on time. But this question is only asking about the coordinates. So the answer is 3. The wave function itself has no physical meaning. The value of psi is a complex number, and in general, it has a non-zero imaginary part. For us to associate a value with something physical, the value has to be a real number. So why do we say that psi has all the accessible information about a system? That is because we can perform a mathematical operation involving psi to get a real number. For example, if we multiply psi by its complex conjugate, we get the square of its absolute value, which is a real number. This real number has a physical interpretation. The value of psi star times psi at a given location is postulated to be the probability density at that location. This assumption is known as the Born postulate. So what does probability density mean? Let's take the simplest case of a system consisting of just one particle constrained to move in one dimension. The probability of finding the particle within a very, very small interval between x and x plus dx is given by psi star times psi times dx, or the square of the absolute value of psi times dx. Here we can see the dx has a unit of length. If dx is in meters, then psi star psi must be in reciprocal meters. So that when we multiply psi star, psi, and dx, we get a unitless quantity. Recall that probability is a number between 0 and 1 and is unitless. Anytime you encounter the term density attached to a quantity, it typically means for every unit of whatever variable the quantity depends on. To summarize, psi has no physical meaning. Psi star psi is probability density. For a one-particle system, psi star psi dx is the probability of finding the particle between location x and x plus dx. Consider a one-particle system confined to one dimension. So, the particle's location can be anywhere from x equals negative infinity to positive infinity. Psi star psi is a probability density function. This means that the integral of psi star psi over all possible locations, that is, from x equals negative infinity to positive infinity, is equal to 1. Why? Because we are assuming that the particle exists to begin with. Therefore, we are 100% sure that it is somewhere between x equals negative infinity to x equals positive infinity. If we are 100% sure, then the probability is equal to 1. This expression, the integral of psi star psi over all space is equal to 1, is called the normalization condition for the wave function. We are 100% sure the particle is somewhere in the universe. Consider a one-particle system confined to one dimension. So, the particle's location can be anywhere from x equals negative infinity to positive infinity. What if the integral of psi star psi is 1/2 from x equals negative infinity to x equals 0, and the integral from x equals 0 to x equals 1 nanometer is 0.3? What is the value of the integral from x equals 1 nanometer to x equals infinity? If we represent our locations with this number line, and this location corresponds to our origin, where x equals 0, then the probability of finding the particle to the left of this point is 1/2 or 0.5. Now for this integral, with the lower limit at x equals 0 and the upper limit at 1 nanometer, If this location is 1 nanometer to the right of the origin, then the probability of finding the particle between this point and the origin is 0.3. Finally, let's take a look at the integral that we want to evaluate. The lower limit is 1 nanometer, and the upper limit is positive infinity. This range of x values corresponds to locations to the right of 1 nanometer. That would be this part of our number line. These are the locations that we have not accounted for so far. At the other locations, the probabilities add up to 0.8. 0.5 plus 0.3 equals 0.8. Since the total probability for all locations is 1, the probability for the remaining locations must be 0.2. What if the integral of psi star psi is equal to 1 from x equals 0 to x equals L, where L is greater than 0? What is the value of this integral? Since the integral of the probability density function from x equals 0 to x equals L is equal to 1, it means that the probability of finding the particle between x equals 0 and L is 1. In other words, we are 100% sure it's there. Therefore, the probability that it is anywhere outside this interval is 0. This integral represents the probability of finding the particle at x greater than L, which is outside the 0 to L interval. Therefore, the answer is 0. In fact, we can conclude from the given information that psi is 0 at x less than 0 and at x greater than L. And the integral from x equals negative infinity to x equals 0 is 0. What if we have a one-particle system confined to move in 2 dimensions? This means that the wave function psi depends on 2 coordinates, the x and y coordinates of the particle. Therefore, the integral in the normalization expression must involve a double integral like this. The expression psi star psi times dx times dy is the probability of finding the particle between x and x plus dx, and between y and y plus dy. We integrate twice, first over all possible values of x. The resulting expression will no longer depend on x. We integrate one more time, this time over all possible values of y, and the result should equal to 1. Here's another way of writing the integral. This says taking psi star psi, then integrate it first with respect to x, then with respect to y. Note that the order of integration does not matter. We can integrate with respect to y first, then the result will depend only on x. Following up with integration with respect to x, we get the same result. What do you think is the unit for the probability density function here? Since dx and dy both have units of length, the product of dx and dy must have units of length squared or area. Since psi star psi dx dy is a probability, it is unitless. Therefore, probability density psi star psi in this case must be per unit area. Our probability density here is probability per unit area. Using base SI units, the unit for psi squared here would be per meter squared. Consider a particle confined to move in 2 dimensions. How would you write the integral to calculate the probability of finding the particle in the rectangular area shown here? We can see that the rectangle spans the interval x equals -2 to x equals +5 along the x-axis. Along the y-axis, it spans the interval y equals -2 to y equals +2. Therefore, the probability of finding the particle within this rectangle is this. We would write down the expression for the probability density function psi star psi, then integrate it with respect to x from x equals -2 to +5, then integrate the result with respect to y from y equals -2 to +2. We live in a 3-dimensional world, so to completely describe location, we need 3 coordinates, x, y, and z. It's useful to think of the x-coordinate as how far the location is east or west of the origin, with x being positive one way and negative the other way. Then the y-coordinate is how far north or south of the origin, again with one way being positive and negative the other way. The third coordinate, z, is how far the location is above or below the origin. Usually we take positive values for z if the location is above the origin and negative if it's below. So in general, how do we write the normalization condition for a one-particle system? We just extend the ideas we learned earlier in the one-dimensional and two-dimensional cases. We do a triple integral like this. Here, when we multiply the probability density function psi star psi by dx, dy, and dz, we get the probability of finding the particle between x and x plus dx, and between y and y plus dy, and between z and z plus dz. Then, we integrate with respect to x from negative infinity to positive infinity. The result of this integration will be an expression that no longer depends on x. It will only depend on y and z. Then, we integrate the resulting expression with result to y from negative infinity to positive infinity. The result of this integration will be an expression that no longer depends on y. It will now only depend on z. Then finally, we integrate the resulting expression with respect to z from negative infinity to positive infinity. The result should be equal to 1. Alternatively, we can write the integral this way. We write the expression for the probability density. Then integrate over all possible values of x, then integrate over all possible values of y, then integrate over all possible values of z. As in the two-dimensional case, the order of integration does not matter. What do you think is the unit for the probability density function? Well, dx, dy, and dz have units of length, so dx times dy times dz will have a unit of length cubed or volume. Therefore, psi star psi is probability per unit volume. In base SI, the unit will be per meter cubed. What if we have a two-particle system where both particles are confined to move in one dimension? This means that the wave function psi depends on two coordinates. If we call the x-coordinates x1 and x2 for particles 1 and 2 respectively, then integral in the normalization expression is a double integral that looks like this. The expression psi star psi times dx1 times dx2 is the probability of finding particle 1 between x1 and x1 plus dx1, and finding particle 2 between x2 and x2 plus dx2. We integrate twice, first over all possible values of x1. The resulting expression will no longer depend on x1, but it may still depend on x2. So we integrate one more time, this time over all possible values of x2, and the result should be equal to 1. Here's another way of writing the integral. This says integrate psi star psi first with respect to x1, then with respect to x2. The order of integration does not matter. We can integrate with respect to x2 first, then the result will depend only on x1. Following up with integration with respect to x1, we get the same result. What do you think is the unit for the probability density function here? Since dx1 and dx2 both have units of length, the product of dx1 and dx2 must have units of length squared. Since psi star psi dx1 dx2 is a probability, it is unitless. Therefore, probability density psi star psi in this case must be per unit length squared. Using base SI units, the unit for psi star psi here would be per meter squared. In quantum mechanics, we frequently need to integrate functions over all space. When we say over all space, we mean that the integration for each coordinate is from negative infinity to positive infinity. Writing the integrals can be quite cumbersome, so they are frequently abbreviated. For example, regardless of the number of coordinates the wave function depends on, we can write the integral for the normalization as integral of psi star psi d tau. This d tau here represents dx if the function depends only on x. If the function depends on x and y, then d tau represents dx times dy. If the function depends on x, y, and z, then d tau represents dx times dy times dz. Notice that no limits are specified next to the integral symbol. The lower limit is implied to be negative infinity, and the upper limit is implied to be positive infinity. So, If psi depends on x, the abbreviation shown here means that we integrate psi star psi with respect to x from negative infinity to positive infinity. It doesn't look like much effort is saved by abbreviating. But look how much effort you save if psi depends on x, y, and z. Suppose a function f is such that the integral of f star f over all space is a finite number. If this integral happens to be equal to 1, we say that function is normalized. If the integral is not equal to 1, we say that f is not normalized, but is normalizable. The function is said to be normalizable because we can multiply it by a constant called the normalization constant in order to get a normalized function. So how do we determine the normalization constant? Let's call the normalization constant n. If we multiply function f by the normalization constant, we get the normalized version of function. Let's call it g. Now, since g is normalized, the integral of g star g over all space is equal to 1. Let's substitute nf for function g in the integral. The complex conjugate of g is the complex conjugate of nf, and the complex conjugate of nf is just n star times f star, and g itself is n times f. We can factor out the constants n star and n from the integral, but n star times n is just the square of the absolute value of n. Therefore, the integral of g star g over all space, which is equal to 1, is equal to the square of the absolute value of n times the integral of f star f over all space. It's easy to see the absolute value of n is equal to the square root of 1 over the integral of f star f over all space. What if the wave function psi is equal to some constant n times function f, where the integral of f star f over all space is 25? What is the value of the normalization constant n? Since psi is normalized, n here is the normalization constant. It's the constant that we multiply with f to get a normalized version of f. So, we can calculate the absolute value of n as 1 over the square root of the integral of f star f over all space. Substituting 25 for the integral, we find that the absolute value of the normalization constant n is 1 over 5. This means that n itself can be any complex number whose absolute value is 1 over 5. It can be 1 over 5, it can be negative 1 over 5. In general, it can be 1 over 5 times e to the I theta, where I is the imaginary number, square root of negative 1, and theta is any angle from 0 to 2 pi. In general, wave functions must be well-behaved functions. Note that since we are saying in general, there are some exceptions. So what is a well-behaved function? A well-behaved function has 4 characteristics. First, it should be single-valued. For a given set of coordinates x, y, and z, the function should have just one value. Second, the value of the function should be finite. It should not go to infinity. The function should also go to 0 as x, y, or z goes to positive infinity or negative infinity. And finally, it should have continuous first derivatives with respect to the x, y, or z. Let's examine each of these characteristics of a well-behaved function and see why psi should be well-behaved. Why should psi be single-valued? It has to do with the interpretation of psi star psi as a probability density. Having multiple different values for psi star psi at any given point is clearly absurd. The requirement that psi star psi being single-valued at any given point implies psi itself must be single-valued. Take a look at the function of x shown here. Would you say that this is single-valued? Obviously not. For example, at this x value, we can clearly see that there are 3 possible values for the function. Here, here, and here. Why should psi be finite? Again, it has to do with the interpretation of psi star psi as probability density. This interpretation implies that if psi is infinite at some locations, then a particle has 0 probability of being anywhere where the function is not infinite, but it is certain to be found at all points where the wave function is infinite. Consider the function e to the power kx, where k is a positive constant. In which of the following intervals is the function not well behaved? A, at x less than 0, b, at x greater than 0, or c, at x between -1 nanometer and +5 nanometer. In all of these intervals, the function is single-valued and continuous. So, let's see if there's an interval where the function goes to infinity. It's easy to see that this would be the case when kx approaches positive infinity. So the answer is B. Note that k is given here as a positive constant. So as x becomes more positive, we will be raising e to a more positive exponent and the value of the function becomes larger. Therefore, e to the kx goes to positive infinity as x goes to positive infinity. What about the two other choices? Let's look at choice A. If x is less than 0, then kx is negative since k is given here as a positive constant. Remember, anything raised to the power 0 is equal to 1, and anything raised to a negative power is less than 1. So we expect to the power kx to approach 0 as x approaches negative infinity. The function is well behaved in this interval. What about choice C? In this interval, x does not go to positive infinity, nor does it go to negative infinity. So we expect e raised to the power kx to be finite within the given interval. The function is well behaved in this interval. We can see that the function e to the kx misbehaves as x approaches positive infinity. Otherwise, it's okay. So we can actually use e to the power kx as part of piecewise wave function that is well behaved overall. In other words, psi can be equal to e to power kx for intervals where it is well behaved, such as those given in choices A and C. Why should the first derivative of the wave function be continuous? The reason is that the wave function is postulated to be a solution to a second-order differential equation. The equation is called Schrödinger's equation. The Schrödinger equation depends on what the system is. Here's an example of a Schrödinger equation. This is for a one-particle system restricted to move in one dimension. Solving this equation means looking for the function psi that will satisfy the equation. We'll spend a lot of time in the course on the Schrödinger equation. For now, just be aware that equation involves second derivatives of psi with respect to coordinates. In this example, we see that the equation involves a second derivative with respect to x. So, the second derivative of psi must exist at any given location. In order for the second derivative to exist, the first derivative must be continuous. There are exceptions where we allow psi to violate this condition. These are locations where the potential energy goes to positive infinity or negative infinity. Example: for an electron in a hydrogen atom, the first derivative is not continuous at the nucleus, so the second derivative of the wave function is undefined at the nucleus. At the nucleus, the potential energy of interaction between the nucleus and the electron goes to negative infinity. Consider plots of two functions shown here. What makes these functions not well behaved? Function a is not continuous at this x value. Therefore, at this point, the first derivative does not exist, and the second derivative does not exist. For function b, the point of this function is said to have a cusp. The derivative approaches a positive number as we approach this value of x from the left. The derivative approaches a negative number as we approach this value from the right. The derivative is not continuous. As you will see in a future lesson, the wave function for an electron in the 1s orbital of hydrogen has a cusp at the nucleus. As mentioned earlier, this can happen when the potential energy at a given location goes to positive infinity or negative infinity. Finally, why should psi approach 0 as x, y, or z approaches positive and negative infinity? This has to do with the interpretation of psi star psi as probability density. Psi should be normalized, which means that the integral over all space of psi star psi must be equal to 1. And the only way this can happen is if psi approaches 0 as x, y, or z goes to positive infinity or negative infinity. However, there are exceptions. If the potential energy does not go to infinity as x, y, or z goes to infinity, then it is possible to have what is known as unbound or continuum states. This happens when the total energy is higher than the potential energy as x, y, or z approaches infinity. In these cases, the solution to the Schrödinger equation turns out to be not normalizable. Psi does not go to infinity, but it oscillates following a sinusoidal pattern as x, y, or z approaches infinity. Consider the plot of potential energy versus x shown here. Where as x approaches 0, the potential energy approaches positive infinity, and as x approaches infinity, the potential energy approaches 0. At which of the two energy levels shown here is the wave function not normalizable? The wave function is not normalizable when the energy is higher than the potential energy as x approaches infinity. So that happens at this energy level. When the energy is higher than the potential energy at x equals infinity, the wave function is said to describe a continuum or free state. Note that in this particular case, the potential energy at x equals infinity is 0. The word continuum is used to describe the states because quantum mechanics predicts no energy quantization. Otherwise, when the energy is less than the potential energy at x equals infinity, the wave function is said to describe a bound state. In a bound state, the particle is essentially confined to a finite region of space. In a free or continuum state, the wave function oscillates continuously as x goes to infinity, and the wave function is not normalizable. In the next lessons, we will learn the rest of the postulates of quantum mechanics. We will learn how to use these postulates to extract information from the wave function besides probability density. We will learn about quantum mechanical operators and how they are related to measurable quantities. We will also learn about the Schrödinger equation, which is the equation we need to solve in order to determine the wave functions and energies of a system. Then we will apply the postulates to the simple systems, and finally, we will apply the postulates to atoms and molecules. We will learn additional postulates as well as approximate methods to deal with systems with more than one electron.